morning, everyone. Good morning, everyone. Today we have Patrick Mayerhofer, who is a PhD in biomedical engineering, no, biomedical physiology, sorry, and kinesiology from Simon Fraser University in Burnaby, in British Columbia, which is next to Vancouver. And he is currently a consultant and lead research scientist and co-founder at Weartech Labs, which is a Simon Fraser University core facility. And he has a great interest in wearable technology, machine learning, big data, and everything related to this. And he is working on enhancing and improving these technologies. And this is also the topic of his talk. So now over to you, Patrick.
Thank you. Hi, everyone. Let me first try to share my screen here. Okay, so moment of truth. There we go. Do you guys see the presentation? Awesome. Cool. Okay. Thanks, Alex. Yeah, and thanks for having me today. It's pretty cool. Seeing so many people and especially having like a little bit of German talk right before. That's something new with such a big group for me. Just a little bit about myself. I'm Patrick. I did my undergrads in Vienna. I then did an internship in Calgary and through that moved to Vancouver to do my PhD here. I'm now the lead research scientist at the core facility called Weartech Labs. I'm actually not a co-founder in this core facility. Co-founder is like different things. And we are kind of like starting to become operational right now. So I'm now like building new teams, starting new projects, and creating new collaborations with industry and academia as well. In my presentation today, I would like to talk a little bit about my journey and what I've learned, and mainly talk about, the wearable technologies that I've been working with and what I've learned in wearable technology, as well as how we integrate artificial neural networks and real-time feedback control systems into these wearable technologies to improve like daily lives throughout. If you have any questions, I'm okay with you guys interrupting me as well. You can ask questions in the end, but also I'm totally fine if you have any questions throughout the presentation. Okay, but first I would like to acknowledge that I'm working and living on the Musqueam, Squamish, Tsleil-Waututh, and Coquitlam unceded traditional territories. Just a very quick layout of what I'm gonna go over today. I'm just like to kind of like get us all onto the same page. I'm quickly gonna go over wearable technology in general, then over artificial neural networks and over the real-time automated feedback side. And then I'm going to go over the thesis projects that I did during my PhD, which I finished, I think, in this last December, like about a year ago. And then just a very quick kind of like what's now, like where are we right now with the technology and how are we moving forward with all of this? So when we talk about wearable technology, most people think about these kind of things, like wristbands, fitness trackers, the Oura Ring, and so on. And that's totally true. That is wearable technology. But at Weartech Labs, where I'm working right now, we are talking about much, much more when it comes to wearable technology. Wearable technology, oops, there's something, sorry, I just need to fix something here. There we go. Wearable tech. Oh, there we go. That's good. Yeah, wearable technology can also be hearing devices that can be wearable ultrasound devices, any kind of like biosensors and health monitoring devices, as well as exoskeletons and prosthetics. So we're also working with exoskeletons and prosthetics. They can be powered or non-powered. This thingy here, I don't know if you've heard of this, like it's kind of like from Arc'teryx now. It's really cool. It's for hiking. It's implemented in pants. Really cool stuff. I definitely recommend you guys checking that out. And then wearable technology can also be AR, augmented reality glasses, or human-computer interfaces, like how Neuralink is doing it, and so on and so on. So obviously, there's a lot of different applications. I can't go over all of them. One more that I want to mention is that we here also define the smartphone as wearable technology, not just for its sensors inside, but also for its camera. Like the camera you can bring anywhere, you can put it anywhere, you can film yourself in movements, and you can actually analyze your movements with your phone as well. So we also define that as wearable technology. Now I'd like to quickly go over artificial neural networks. I'm not planning on going too much into detail of how they're working, but just for people who are completely unfamiliar, artificial neural networks are loosely inspired by the brain. So they're basically these layers of these connected nodes. And through these connected nodes, they can automatically learn an input-output relationship of data. So the cool thing with those is that they can automatically learn complex patterns in the data without us kind of like having to do very specific changes within. And so when I started my PhD in 2018, there were a couple of, I would say, important variations in neural networks that were pretty big and used a lot. The first one is the recurrent neural network, or in short, RNN. RNNs are really, really good in understanding sequential data. So they can, for example, understand text or sounds. They can predict different data like stocks, which does not work that well, but like a lot of people still use it for that, or the weather, and so on. And the second one was the convolutional neural networks. And convolutional neural networks got extremely famous because they became really good at understanding images. One of the very first big things was distinguishing between cats and dogs. And then all of a sudden, they could basically understand almost everything that is happening in an image, could detect different objects in an image, and are now as far as like actually detecting moving moving objects in videos and so on. So that those kind of like are the two bigger ones, and I've used them throughout my PhD. But in the end, I'm also gonna go a little bit into like what's happened since then, because that is an extremely fast moving like industry, especially right now. I want to quickly also explain how feedback control works, just to kind of like also that we're all on the same page. In general, in feedback control, we have something that's called a plant. Can you guys see my mouse? Okay, cool. Which is the plant. And so the plant has usually some kind of output. And let's say, for example, now let's talk about cruise control. In cruise control, the plant would be the car, and the output would be the speed that we are driving with right now. Usually in cruise control, we have a target speed, a target output, and then a feedback controller compares the actual speed with the target speed, and then feeds this error into a controller. The controller calculates the error, does some different calculations in there, and then inputs a new input into the plant. In cruise control, the input would then be, it would change the power input into the like electric motor in the electric car, and so then change the actual speed that we're driving with. Real-time feedback is really cool and can replace a lot of human activities, and we sometimes don't even realize anymore like where they are in our lives. Like for example, thermostats to control the temperature in the houses, like cruise control. We now have self-driving cars, but also airplanes are like in most cases, most of the path flying by themselves because of automated real-time feedback. In my PhD, one of the bigger topics was kind of like feedback control in sports. When I started in 2018, I was really into sports, but we kind of like always use sports as like a proof of concept, and it can always be applied to other concepts like health technology and so on as well. So to give you a little bit of an idea of how we can implement these three technologies, so wearable technology, artificial neural networks, and automated real-time feedback, I'm going to give you this example of coaching. So typically we have an athlete that does some kind of like sports. The coach looks at the movement, they observe the movement, and comes up with an actual performance based on what they're seeing. Then the coach compares the actual performance with the target performance, where they would like the athlete to be. They see the error, and then they give feedback to the athlete. Okay, so now to automate that, we could now say, okay, let's use wearable technology to measure the athlete. We can have a lot of sensors in the body that measure movement, that measure heart rate, that measure skin temperature, and so on and so on. So we measure the athlete, and we can then use models to analyze and interpret these measurements. Here, we can use neural networks, and I'm going to get into this later, but we can also use like what we call physics-based models, where we have more variables that are actually from the real world. And then we have the actual performance. We compare this to where we would like the performance to be, and we can use a controller to automatically compare these performances and give automated feedback to the athlete. That's kind of like the big conceptual model of where this could fit into sports, but you could like, again, like just implement it into health as well. So quickly to talk about like why I was working on this and what motivated me throughout my PhD to kind of like follow this conceptual model. First of all, there is not a lot of automated feedback control systems in sports yet. And that's really interesting because Also, when I already started, wearable technology was already really, really advanced. For the longest time, we did measurements of people in health and sports only in the lab because our equipment for measuring with wearable technology was just not good enough. Wearable sensors were inaccurate, didn't have enough computational powers, the battery wasn't good enough, and so on. But in 2018, when I started, these wearables in general became more and more state of the art. So we can actually now use them to accurately measure movement. And so I looked a little bit more into why do these things not exist more when like all these technologies are there. Like we have models, we have wearable technology, we have automated real-time systems. And one thing that I found is that first of all, with models, um, they are extremely complex to develop, but also extremely hard to generalize. Even with neural networks, especially back then, you would train a neural network for one move to understand one movement that might work, but the moment you want to use it for something else, you need new data and you need to like develop a new model again. You can't easily generalize it to like all the different movements, and it's a lot of work and a lot of data. The same with feedback control. Developing feedback control systems is fairly complex, and I'm gonna get into this in a moment. And again, they're very hard to generalize. When you develop a feedback control system for thermostat, you can't then use it for cruise control as well, because that's a completely different problem. So you need to kind of like solve a new problem for this specific feedback control system. So the objective of my thesis was to develop and test the tools that can simplify the process of gathering data during sports, analyzing these data, and providing automatic real-time feedback to the athlete and the coach. So basically, I was not aiming to develop one big feedback control system for a specific sports, but rather developing the tools that can then help scientists and companies apply them more easily to their own products. And so for this, I did 4 different projects, where in the first one, I developed a feedback control system to control control power in cycling. A second project where I compared a physics-based model and a neural network model to better understand the advantages and disadvantages of a neural network to create these models. In the third project, I aimed to classify the running performance from running patterns. And in the fourth project, we developed a remote wearable technology course for human data collection. So let's start with the projects. And I'm going to start with the first one, where we developed the feedback control system. So again, this is kind of like the conceptual model of how feedback control works with the plant, the actual output, the target output, and then the controller comparing these outputs and inputting the new input to the plant. And my goal here was to develop a stable feedback control system. Oh, sorry. The problem that I've mentioned before was that it's really hard to develop these systems because they're complex and they're hard to generalize. The thing with the controller is that there is a couple of different settings that I don't want to go into detail that are always very specific for a specific problem. So when I want to create a new feedback control system for cruise control, for example, one solution would be that I put a setting, I try it out, see how it works. I come back and I try it again. And I kind of like go back and forth. It's extremely time inefficient and takes a long time to come up with the best controller settings for a specific problem. There's different solutions, but they're all fairly complex. So we try to simplify this with with our project. So yeah, we try to simplify this approach for the closed loop feedback system. And in our case, we use cycling as this proof of concept, where our plant was the cyclist, and we tried to control the power, so basically the watts during cycling with the commanded cadence. And so there were 3 steps that we went through in this project, where the first one was we tried to develop a plant model. So the goal was to develop a model of the cyclist, where in the model, the cadence was the input and the power was the output. Not going to go into this model here, just have it here that you guys can see where this goes now. So we then took this model, after we validated it, we took this model and put it into a simulation of a full feedback control system. So in this simulation on the computer, the model of the cyclist is replacing the real cyclist, because you can put a real cyclist into the computer. And it's basically simulating how the cyclist is taking the commanded cadence and then outputting the power. And this simulation on the computer now compared the power with the target power. And then here are the settings within the controller and then commanded the new cadence to the cyclist model. The cool thing with this now was because we now had the simulation, we could basically create new settings again and again and again, and just basically like optimize for the best settings on the computer without having to go back and forth with a real cyclist to find the best settings of this feedback control system. And then the last part of this project was to actually take this feedback control system, put it into a microcontroller system, like into a real product, basically, and test it outside with a real cyclist. So here now, instead of the model, we actually have the real cyclist again. We measure the power, we compare it to a target power, the controller then changes the commanded cadence, and the cyclist tries to react to that. And so this experiment, which is one of the 3 experiments we did through this project, is the one where I'm going to show you how we did it with basically like a little bit of a graph. We had a microcontroller in the back. The cyclist had earphones where he heard the commanded cadence through a metronome signal. And then we measured the power on the pedal and the cadence as well. So this graph quickly shows how the experiment was set up. We had the cadence, or the cadence here is the top graph and the power is the bottom graph. And so the goal was, so this is the target power, and we had these step changes. So the power was like solid, then less for a moment, solid, and then more, and then solid, and so on. And based on this target power, the feedback controller now commands the cadence to the cyclist. So you can imagine you're sitting on the bike and you're hearing this signal, and you're kind of like trying to follow that signal as closely as possible with the cadence. And so just to show you the result, this is basically the actual cadence of one participant trying to follow the commanded cadence. And based on this, the power of the bike, the watts output is changing. And without the cyclist ever looking at a display where they see their own power, where they see the target power, they were able to follow the target power pretty well. I'm not going to go into the stats of this, but the result was they were pretty accurate and pretty spot on with how accurate the cyclists could ride their bike with this system. So in conclusion for this project, we used plant simulations to optimize for the closed loop controllers, and actually were able to develop a fairly stable feedback control system, which simplified the development of this whole feedback control system. Cycling with feedback control enabled the accurate tracking of target power. This could be interesting in products like extremely accurate training, where a cyclist wants to do, for example, interval training, and they want to have high power, low power, high power, low power. And instead of having to look at a display the whole time, they only need to listen to the metronome, or in a better case, to actually a music rhythm, for example. Obviously, the development of the plant model could be much simpler. If you remember, this was the model, and it's not like it's not a simple thing. If you just new to model development and so on, this is not something that everyone could just pick up and do in the moment. And that's what I'm gonna get into in the next project. And if you're interested in like the details of this project, obviously this is just a very quick summary. Then you can check out our proceedings paper from a conference a couple of years ago. That was the first project. In the second project, we compared a physics-based model with a neural network model. So let's now come back to this physics-based model that I just showed to you guys. My goal of this thesis was to simplify the development of automated real-time systems, but obviously creating this kind of model is fairly complex. So we thought, why don't we just try to compare this physics-based model with a neural network model. For the neural network model, we really only need the data, and we see if it can actually learn to be as accurate, as good as the physics-based model as well. So the goal was to understand the advantages and the disadvantages of the physics-based and the neural network model in predicting the cycling power. So now we don't have the full feedback control system. We really only have the commanded cadence. The cyclist is trying to follow the cadence, and we have the power, and the models are trying to predict the power based on the commanded cadence of the cyclist. Let me show you what the experiment for this project looked like. Again, we have the cadence on the top and the power on the bottom. And so now the commanded cadence was actually these step changes, where you can imagine it sounds something like, and then all of a sudden within like immediately it's like much quicker, and the cyclist is trying to match this as quickly as possible. So we can then measure the actual cadence, and based on that, we can also measure the watts, the power of the cyclist. And the goal of both models, the physics-based and the neural network model, was to take the cadence and predict this power as accurately as possible. Let me quickly compare this. Here you have in both graphs the power, in both graphs the same actual power. And for, I think it was like 18 participants, sorry, about 18 participants, we had an average normalized root mean square error of 19% for the physics-based model and about 18% for the neural network model. So the normalized root mean square error was fairly similar. I also want to mention here that these normalized root mean square errors are pretty big. Like it sounds like, well, that's like not really not good. One thing that is important to mention here that the main goal was to compare them, but we were riding on like a mountain on a running track, and it was very windy up there. So like you could imagine like on one side you have headwind, on the other side you have tailwind. So basically, even though the cadence would stay the same, the power is always changing depending on whether you have headwinds or tailwinds. And we didn't measure the winds, so the models, both models, did not have that extremely important piece of information for the model. That's why both of them weren't super accurate. But what we found was that with the information that they got, the neural network was able to learn as much as we actually as the physics-based model could do as well. So the conclusion here was that the physics-based model and the neural network model had similar prediction performance. The neural network model really helped us develop these complex models. It's much, much simpler to develop the neural network model than the physics-based model, especially if you know how to use like, keras in Python. Like it's like nowadays using these models is much simpler than actually understanding the physics behind it. But the physics-based models are much more physically meaningful. And I always want to mention this in the end because obviously, like when you develop a model for any kind of like problem, you first want to think about what is really my goal. Do I want to develop it as quickly as possible and as simple as possible? Or do I really want to develop it to understand what's actually going on? Like if you really want to understand it in the real world and why something is working and why something is not, a physics-based model really has its advantages as well. And you can read that paper in the Journal of Biomechanics. Again, much, much more detail if you go into that paper. A third project, it's kind of like a little bit of gear shift where we try to classify running performance from running patterns. Let me give you a little bit of a running specific background to kind of like also get you in the headspace of why we did that. First of all, running patterns, like changing running patterns might be one of the ways to improve performance. So it's kind of like a technique. In most of the sports, there's a good technique and there's a bad technique. Same for running. But interestingly, it's like this exists. There's enough evidence for sprinting that there is a good technique versus a bad technique. But for some reason, it hasn't really been proven well enough yet in long distance running. So we actually have no idea whether there's a good technique in long distance running or a bad technique as well. Like people run and we can't just look at them and be like, yes, this is a good technique. It's so far, there's no conclusive evidence at the very least, let's say it like that. So the goal for us was, okay, why don't we take a lot of data and a very state-of-the-art neural network, and we try to take this data and make this neural network trained to predict someone's performance based on the running technique. Just see, could it do it, yes or no? And if yes, then we can look more into why not? And if it can't do it, I mean, then like, yeah, that would be our evidence now that it might just not be working. The problem that we've got here is that, let's say now we predict for performance and the model just simply can't do it. Does that now mean that there is no good or bad performance? Or does it mean that our model was just not able to actually find these patterns in the data? Or does it mean that the data actually just wasn't good enough, right? So that's always a little bit of a problem in neural networks that, like, if it doesn't work, it could always be that you were just not a good enough researcher to make it happen with your neural network. And remember this, like we tried to find a solution for that as well. To give you an idea of how we collected the data here, we had 119 participants run on a treadmill with 3 different speeds, as well as with their preferred speed on overground. And they had this like IMU sensor in their insoles. For people who aren't familiar with IMU sensors, like it's these like really little sensors that can measure accelerations in all 3 dimensions and angular velocities in all three dimensions as well. And so what we did, we actually took this signal from the accelerations and the angular velocities, and then we created a spectrogram. A spectrogram is kind of like a frequency analysis over time of the signal. And we did that because we used a state-of-the-art image recognition algorithm to actually learn from this data. More particularly, we used ResNet for people who've used that, because ResNet at this point was just like one of the most advanced image recognition algorithms. And they have also proven at this point that it can analyze really well these time sequential data that are transformed into spectrograms as well. Like, for example, they analyze bird sounds and speech in general with spectrograms. So we're like, let's try this for our problem, basically. So let's come back now to this problem. How do we know whether there is no good or bad running pattern, or whether we are just not good enough with our neural network to do that? To solve that problem, we decided to first try to predict who is running. Can we train our model to predict who is running? Because that's at least some evidence that it can learn from the data and that the data has some information in it. And then if yes, if it can do that, then we use the same model to train it on can it actually detect a good versus a bad running pattern. And so for who is running, we had 119 runners, and we left out 24 runners to then try to detect whether they can, who it is. And we had 84% accuracy. So 84% accuracy when you have to decide between 119 different runners, that is pretty good, especially in the industry that I'm working with, where 119 runners in general is a pretty big data set. And we trained it on treadmill data and tested it on overground data, meaning that the data is fairly different on the testing data is fairly different compared to the training data. So that's a pretty good result. So at this point, we were fairly confident that our model is actually able to understanding and on finding patterns within the data. So we were like, okay, cool. Now let's create the most simple experiment to figure out whether it can compare fast versus slow runners or the performance. So we asked people to give us the 10K current personal best, and that was their performance. And instead of letting the model predict their actual 10K performance, we just put them into two buckets, fast runners and slow runners. And we're like, just tell us, is it fast or slow? So it's basically a 0-1 kind of like problem. That's the simplest problem that we could come up with. And we found a 57% accuracy with that. So that's basically as good as a coin flip. So we were not able to actually predict the performance as well. So what we can say at this point is that, yes, we're able to predict who is running, but we're still not able to predict how well are they running. And this might be like just another piece on top of this inconclusive evidence that that might just really not be a good versus a bad running pattern. So to conclude this here, we found that an image recognition algorithm could actually identify runners, but it actually, and it also generalizes to different environments. Like it could be trained on treadmill running with 3 different speeds, and it could then detect who is running on overground running, which is slightly different, which is also like a fourth kind of like self-chosen speed. But the algorithm was not able to classify slow versus fast long distance runners. And if you want to read that paper, it's currently in review, and hopefully you'll be able to read it in the Journal of Biomechanics soon. Okay, so that was the third project. And so now quickly to the last project. And so to give you a little bit of an idea of why it came to this project, it wasn't really planned. I was actually during this time between project 1 and 2, I was doing an internship at a wearables company, but then COVID hit. And as you can imagine, most of universities, like in physiology departments, biomechanics departments, the laboratory courses are extremely important for the students. Like they need to take them, they need to learn how to measure physiology, measure heart rate, muscle activity, and so on. And when COVID hit, no one could go to the labs anymore, which means that all these students couldn't take one of their most important courses, they couldn't finish their degree, they couldn't move on with their degree. So the department asked me if I wanted to help them and develop kind of like a remote wearable technology course where students still get this hands-on experience that they can move forward with their course. So I agreed, and this project is not that much of a scientific project. It was more like okay, we need to get a solution for this as quickly as possible. Can we do it? I'm gonna explain to you how we got from basically nothing to a course and what the outcome of this course basically was. For a paper that we then also published, we also tried to a little bit understand remote teaching in general. And what I actually didn't expect is that remote teaching is actually really effective. It's much more effective than I think most people would actually think from just kind of like thinking through it. And remote teaching also has this big advantage of being very accessible. Like people who can't come to university for health or any other issues can still be part of these courses. That means that more people can actually learn something really helpful. The only issue that we're having is that remote laboratory courses are obviously very challenging because like it's much, much easier to bring the students to the lab than the lab to the students, as most labs are extremely expensive and we can't send a lab to every single student. So the purpose of this project was to develop and test an effective remote laboratory course for human data collection and analysis. And to do this successfully, we first came up with 4 course principles that we wanted to base our decisions that we would make out afterwards on it. So first of all, we wanted to enable remote laboratory experience. We wanted the students to be able to have an actual lab experience, actual data collection with actual equipment. We didn't want students to need previous coding or electronics experience. Most physiology students don't have that much coding experience, haven't worked too much with electronics. So we needed to make sure that they can still use this course without all this background knowledge. We wanted the resources to be relatively inexpensive, that students can easily purchase it and use it at home. So the goal was to keep it at the price of about a course book. We wanted it to be all the resources to be customizable, so that that other lecturers from other universities could take our resources and adapt them for their own needs. Oh yeah, that was the last one. And so based on these principles, we came up with these couple of resources. First of all, we developed a lab kit with commercially available sensors. That was kind of fun. Like it got a lot of budget, could just order like all the stuff to my home because I wasn't really allowed to leave my home, and then just play around as much as possible and come up with solutions that we could actually measure physiology with cheap sensors. So this is kind of like an overview of the sensors that we used in the end. It was like a package of about this size, very small, cost about, I think, $150 in total. But it had EMG sensors, so it could measure muscle activity, it could measure heart activity, we could measure movements with accelerometers, and so on. We then used open source software, so Python. Sorry, there someone. Oh no, okay. We used open source software like Python and Arduino IDE that everyone can use it, and we shared all of our code on GitHub so that people can basically just take it as they want, but they can also adapt it very easily for their own courses and their own needs. And then we created Google Docs manuals because it's really easy to publish them online, that people can read them, but people can also copy them, change them, and create whatever they would like to do with it. And then in the end, we created a lot of video tutorials so that everyone can just go through the whole course by themselves at home, at the university, but also just in private if they would like to. Right, so and with that, we came up with 4 labs. The first one was data acquisition analysis, just a general overview of how we collect data. The second one was ECG, so that's heart activity, electrocardiography. The third one was EMG, which is muscle activity. And the fourth one was activity classification. And this picture here, you can see like one of my favorite labs, which was activity classification, where we basically created a fitness tracker on the wrist. And then we would classify whether people are walking, running, sitting, or standing, but we would also count steps with them. So that's basically what a very, very simple Fitbit did in the very, very beginning of its activity. And then we also did a very quick kind of a questionnaire with all the students, like 107 students in the first 3 semesters, and just asked them what they learned, how they liked it. And the standard student evaluation gave us a 4 out of 16 out of 5, which is fairly good for courses in our department. And the qualitative summary was that the course was very challenging, but it was valuable, and students learned a lot about the kind of like the basics of how this data collection actually happens from beginning to end. So to conclude, students can learn important hands-on lab skills remotely, like it worked for us. This course enables an affordable, customizable, and accessible lab course. It also opens this potential for new experiments in the teaching scene where we could now compare teaching lab skills remotely and in person with kind of like the same resources. And you can read all the details about this paper in the Advances in Physiology Education. So that was the last project. I'm seeing I'm kind of like on time. So the conclusions are just really summarizing all of the stuff that we just basically talked about. But what I would way rather very quickly go over is kind of like what's new. So when I started this PhD, like especially in neural networks, we had like a neural network was always very specific for one specific problem. And then when you had a new problem, you needed to create a new neural network for the new problem, right? And then all of a sudden, we got these things called generative predictive transformers, which are all of a sudden these models that have this general knowledge about a lot of things. And just to give you an idea of how quickly they're currently growing, and a lot of people might know that, but I still think it's fairly like interesting. Like in 2019, when GPT-2 came out, the model that none of us really got, I think, kind of like knew, it had like 1.5 billion parameters. Parameters are the things where they basically can store the information in a model. GPT-3, the one that got famous, had 175 billion parameters, which is insane. But then all of a sudden, we didn't just have this model that had all this knowledge. All of a sudden, we had these what's called multimodal models. And if you go now on premium version of GPT, like you can actually try now a lot of different things. It can all of a sudden understand your voice. You can talk with it. It can talk back. It understands images. It understands videos. So all of a sudden, we now have models that really understand like all these different resources. And especially in biomechanics, the holy grail for the longest time was to be able to film someone and understand the joint angles, for example, very accurately of movements. But now this has totally changed because, and I think most of the industry hasn't really gone into that direction, but um, these multimodal models now understand movement so well that it can sometimes give you direct feedback already. It doesn't even have to get the full like joints. It's basically like, hey, your deadlift, like in if you're in the gym, is good or bad for these reasons, which is really crazy. And we're really going now into the direction of trying to understand how good these models are now and how well we can actually use them for our research as well. And there's not just GPT, there's also Llama with Meta, which is open source. There's Claude. Like these models are getting insane. And I urge everyone to look a little bit into it and try to understand what you could actually use this in your research, because I really think that these might be the future and they're moving extremely, extremely quickly. With that, I just want to thank you. Please connect with me. You can connect with this QR code. Actually, my journey in Canada is kind of like at an end. I'm moving to London in January. And I just also wanted to share that I'm moving to a pre-incubator. So basically, a pre-incubator is something where I'm basically being paid to find problems that still exist in our society and find solutions as quickly as possible and create these solutions. So I would love to connect with you guys, like hear your story and like talk a little bit about throughout your daily life or your job or whatever. If there are some problems that you're facing where you're like, man, I wish there was a solution for this. And I could also like, I think that could create really cool connections between us as well. So anyways, thank you for that. And yeah, I'm open for any questions. I've got time.
Thank you very much. This was extremely interesting. Are there any questions?
I have a question if there's nobody else. Nobody closer to the field.
Oh, Stefan? Yeah.
Thanks, Patrick. It's really interesting. I want to play devil's advocate a bit here because that's sort of the most fun things that we can do. On the one hand, I was a bit surprised that basically a lot of the research that you've been telling us here is about what I consider is a basic design cyclist. Would you agree with that? I mean, that's things we did in the early 90s. I did in my HTL with a microchip with 4K ROM that we burned on. So where would you say, you probably didn't focus on this, but where would you say is sort of and then I want to combine this with what, 2015, I went to Sweden for a chair. In Gothenburg, they were then big on wearable technology. And there the issue was more like, how do you get the sensors into the clothing that it looks good, that it's not too heavy? But that doesn't seem to have been an issue really from your research. Is that right? Or is it something you haven't shown us?
I know. So yeah. So first of all, that's a very great comment, and I think it's a very good comment because I totally agree with this. And this has been throughout my PhD. Also, always a conversation with a couple of supervisors on my committee as well. Like a couple of supervisors would even be like, "That's not a PhD research," and I would actually agree with that. With my luck being that my supervisor himself really loves to just think about, what are products, what are the problems that we want to solve, rather than, what is the deepest kind of like research that we need to do right now. And I'm also very much interested in like how can we simplify things for people that create things as quickly as possible. So, and I, during my time, I went to business school, and I'm also now like moving away from academia because I'm much more interested in like finding solutions rather than like the ground research. So I totally agree with you with that. I personally really liked the stuff that I was working on, and like I published it in the end. So I think there
It's
was
cool
still
stuff.
something
It is.
relevant.
It is like, don't get me wrong. It's really very
Oh,
nice. But what I wanted to ask you more precisely is like, you will have a very crucial role because you'll be the one who brings things, who develops products, who rolls it out to market, the big clothing change or whoever will buy this. And for that, I wonder if, there's a few, we've been tricked by our capitalist system. There's something, I'm a linguist, there's something in the language about boosting everything. And so now we don't even realize the metaphors and all the sort of, exaggerated claims that we take for granted. And I want to point out in this context one word that you used. Sort of, you said the AI understands. Does the AI really understand, or is this a metaphor that tricks us and then blows up a bubble? And I mean, it's all very useful. Don't get me wrong, but I still, as the humanist, I have to introduce sort of this critical angle, and I wonder what your comments on that is. Does the AI understand? Is AI even the right term? What does the AI do when it has 175 billion data points? What does it really do when it gives a recommendation that seems to fit? Like, can you speak to that a bit?
yeah, yeah. And so I need to say, when I speak to that, this has not a lot to do with my PhD anymore. That's more kind of like my personal interest, like afterwards. And like I'm using it in my research now as well. But like when it comes to like specifically these like super cool AIs, especially for your question, it's very philosophical, I think, whether they actually understand or not. Because I agree, like I don't think understanding is probably the right word, and I almost need to apologize that I've used that word, because I'm totally on your side that it doesn't understand anything that it wasn't taught by like us humans. With a small but, where we're getting closer and closer now to these models that have not like that kind of like start, it's called chain of thought results, where basically, like, I don't know if any one of you guys is using O1, like this new preview model on premium, where it thinks much longer, and it gives you kind of like a chain of thought of like why it came to the solution. And it's been solving a lot of these problems that before ChatGPT was not able to solve yet. So we're getting closer to a point where it can kind of like think through problems in a much more realistic way rather than just giving you the facts. And that's kind of like the next big problem, to do that solidly. And we're like, the interesting thing now, like there was this like law of scalability, like where basically at the moment you had a bigger server, a bigger computer, a bigger model, you could just train it more and it just knew more. And I think Sam Altman recently gave an interview saying that this is actually now ending. Like even if we have bigger models, they're not going to get better anymore. And now we're back to developing models in a way where they can like understand problems better with their own agency and solve problems with their own age. That's kind of like the next big step that we're hoping is going to happen, but we have no idea when and if that's going to happen. O1 is getting closer to that, but it's still far away from solving a problem that hasn't been solved yet, basically. And so I think as long as that doesn't happen, I agree with you, understanding is probably the wrong word.
Yeah, but I also want to like tie this back into sort of the boosterism that we all sort of fall prey to. And I think you really will have a crucial role. So I really hope we stay in touch. We can discuss this because whatever words you use, and then when your PR guys come and say, "Oh, we can call it understanding," you should be the one I think say, "No, no, 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 no. This is machine learning." So we know this whole AI thing is probably it's too late now to change that, but so you would have very important leverage functions here. But anyway, I want to clear the stage for somebody else to ask a question. There's lots of things we can follow up on here.
I love that, Stefan. Thanks for that.
Yeah, I would have a couple of questions also, if you don't mind. For those who don't know me, my name is Manuel Weber. I'm a researcher, postdoc researcher at this point in computer science at the George Washington University in Washington, D.C. And my research deals with a couple of like similar topics that you mentioned in the talk, specifically wearables and AI. And I do augmented reality solutions for healthcare, specifically focusing on remote medical procedure training. And so I guess my first question is about the first projects you talked about and cycling. So and the results there look pretty encouraging. So I was wondering if you can use, if you think about like the possible use cases, is this like a useful product for competitive cycling or more like for hobby sports? Like where do you see like the applications given that the results look pretty good?
Yeah. So, let's see. You mean this project here, right? Basically this
Right.
one.
So first you tried exactly the feedback system and then with the AI as well. And they're both like pretty encouraging, like the results, right?
Yes. So, it's a great question, and like I think it's like that's actually the project that I started with. It was my very first project during my PhD, and so my supervisor, he had a company called Control Freak, where they before that actually developed a system that could control your running speed based on your step frequency. You could actually listen to music, and the music would change based on if you should run a little bit faster or a little bit slower based on the target speed that you would like to run. And so the company aimed to do that not just with running, but then also with cycling. And so it was fairly encouraging with running. They sold that to a running company at some point. I'm not sure if that's public yet or not. For cycling, I agree that could be a really cool implementation in terms of like product for cyclists, and I think specifically for highly accurate training with professional cyclists. I need to say though, like the results here we're basically more accurate than a recreational cyclist. We weren't more accurate than a professional cyclist. Like professional cyclists are so good in feeling how accurate their power is that we would have to work much more on this specific model to optimize it to make it even better for professional cyclists. That could have been a goal in my PhD because I was really more focusing on developing the tools to create these different systems. I then did not work on optimizing it more to make it more and more accurate, basically. So right now, good for recreational cyclists who want to get better with like music in their ears or so on. Like you could create like more of a recreational product, not for professional cyclists yet.
That makes sense. A quick follow-up on that, since you're talking about feedback control systems there. And again, like I work on the wearable AI combination, but not really haven't really used feedback control systems. I'm aware of the concept. So I'm just wondering in general what your thoughts are on what the strengths and the benefits are of those systems and including them with these kinds of applications and possible other applications you could imagine besides cycling and running.
So I guess like you mean like what are the potential applications for feedback control systems like on a more general kind of like scale?
Exactly. Also in combination with wearable and AI. Yep.
Yes. So I can give you a couple of products that are or not products, more so kind of like research that has been done in different areas. So one, for example, is there is running systems that help that there is a fully fledged system where and this has been like a long time ago for me, so I wouldn't be able to tell you right now who developed this system. There's one team in the Netherlands that created a system that decreases your impact during running. So during running, when you're having a hard heel strike and like you have too much impact, you actually like have a lot of impact on your knee, and that might lead to knee injuries. So what they do is they they increase your step frequency. And if you have a higher step frequency during running, you have a lower impact during running. And so they kind of like have this feedback control system in your ear. And I don't know what the exact signal is, but by using this, you can decrease the impact and decrease your chance for injury. That's, for example, one feedback control system that I can see. Another one in running is a system that takes in your whole kind of like Strava knowledge, and it understands how often do you run, like how high is your heart rate, what are your results from the last races, and so on, and then uses this and develops a little bit of a training program to become better based on the goal that you're having. Let's say you want to run a marathon at some point. It uses all of this information and then creates a solution for that. I also have seen solutions which are much more technical in volleyball. They would use cameras or not cameras, I think sensors on the body, and measure their movements. And the whole feedback control system, you would basically then just walk by the screen every once in a while during your training, and it would tell you how to change your movement to create a better movement, which I think is a really cool application, because in a lot of, like in a volleyball team, like you usually train with 15, 16 people, like 12 people are usually on a team, 6 are playing. Imagine you have a coach and a co-coach. There's no way for 1 or 2 people to look at 15 people simultaneously, but the players could like always double check themselves on the screen and see what they are doing wrong and what they're doing right. So, right, you could create a much more efficient way of coaching by doing that as well. Does that kind of like answer your question? Those are just a couple of examples. We could talk much longer. Like
Absolutely. Great. Yeah. No, thanks again for the presentation. Was fantastic. And yeah, and definitely also keep a lookout for LLMs and how they can be used for those applications also. I guess that's your message as well.
Cool. Yeah, thanks, Manuel. Yeah,
Thanks.
definitely. I think that's where, like right now, where I'm looking more into how can we actually use these like new big models to implement them, right? So like one thing that we're using right now is the vision models of OpenAI to see how well they're actually understanding, in our case, a muscle up. Like a muscle up, is like when you have the bar and you try to pull yourself up and then push, an extremely technical movement. And we're trying to see how well do these models understand it by itself without us having to fine tune it. Does it understand what the person is doing wrong and how it could do it right? Which is something that mainly only coaches can do. And we have been very surprised on how good these models are in understanding these complex movements already, basically.
Patrick, I have a question. And this is Alexandra. A lot of people go to the gym. A lot of people get hurt in the gym. So that actually seems to me a perfect place to develop something that gives real-time feedback when you work out, how you should correct your posture, right? It's like to prevent injury and to also maximize your workout. Is that a possibility?
Yes, and it's actually something that I'm kind of like working a little bit on a more product side rather than like the research side itself. Like I'm working with a couple of physiotherapists in Austria right now. Like the product problem that I'm seeing is in the gyms, it's not really possible because you're filming a lot of people, and that's just on a privacy standpoint not possible. So you would have to target people that are training more by themselves without other people in the background. So physiotherapy, where you come in and then the physiotherapist shows you your movement, and then the physiotherapist is like, hey, take this app, do this movement the whole week, but use it to kind of like that you get feedback throughout the week until you come back next week, right? So that's, I think, a good application, because usually when it comes to physiotherapy, a lot of people just do it at home on the yoga mat. What we're kind of like having to figure out at some point is who pays for that. Because if as a patient, I'm already paying for the physiotherapist, I'm usually not willing to also pay for another application. So you would have to work with insurances and so on. So I think it's that the paying side is one thing on the product, in the product stance, that makes it a little bit more complex when it comes to physiotherapists and like these kind of like feedback systems. But I totally agree. This could be a really cool implementation, and I'm kind of like working on that right now.
Because including building in sensors in clothing, where you don't even have to film it. It's just you measure it.
Yeah. And so sensors, that actually does exist as well. Like there's a couple of companies that do that as well. With sensors, you run into the issue, it's much more expensive. Like, so the cool thingy with video, with what's called computer vision, is that you can do it extremely cheaply, and people can use their personal phones, which means it's only software, which means you have to pay almost nothing. The moment you implement sensors, It becomes, first of all, much more complex for the data analysis because people have like different bodies. You need to be sure like where the sensor is put and so on, but also they need to buy the product as well.
That makes sense. Thank you.
Thanks
I
for the
have a
question.
question. I'm a ski racing coach, and it's going through my head. How could you do this? For me, I wish would be if a parent comes and says, "My kid is too good for this group. I want to have this kid in a higher group." To show them a video and say, "This, this is level this, and this is what my very smart software says. It's just me being biased towards your child." Do you think that would be feasible? Something like that?
I'm not sure if I fully understand. So basically, let me try to repeat this. So you're coaching kids, and some
Yeah.
parents would like a kid to be in a different group, but you would like
Absolutely.
to prove them unbiasedly that this child is actually in the correct group.
Correct.
Oh yeah, cool. Yeah, totally. That's for sure. Like I think that is something that I actually think would be fairly, I don't want to say straightforward because it's not that easy, but definitely possible in a much simpler way, since basically a year ago compared to before that. Yeah, so definitely possible to do depending on like what movements and so on, but yes, that could be possible.
Okay, thanks.
And I like that that's the way that the direction that you're going, kind of like I want something unbiased because people always think I'm subjective, but I need something objective. It's a great one.
I would have one last question, I guess. It's after 10. So in the equation for the power of the cyclist, the only
Yeah.
parameter that it's related to the cyclist is the mass, but I don't see anything such as leg length. You have like, you have cadence and pedal crank,
Yeah.
arm length, and wheel. Why are the physiological parameters of the cyclist not present in this equation?
Because in terms of power output itself, it doesn't really matter.
Okay.
So like it does matter. The size of the person, for example, would matter for the drag, like for
Right.
like the drag coefficient, which is actually something that we have. We have a drag coefficient somewhere. I thought, wow, this has been a long time. Oh yeah, there we go. There's the C. We have drag coefficient, but we actually optimize the drag coefficient with the person itself. So we don't have to measure their sizes. We let them cycle. And based on what we measure, we can then estimate their size. Basically, we're not even estimating the size, we're just estimating the drag coefficient. Leg size isn't that important because it's more like cadence to power with the weight and the shape of the person. Those are the most important pieces.
Okay. So translating, so you would say a taller person doesn't need a longer crank and a shorter person doesn't need a shorter crank arm length.
No, they do. They do.
Yeah, so that's why I'm wondering why they. Okay, yeah.
But then the crank is changing, right? So
that
doesn't. Yeah.
Okay, I understand. Yeah. Okay.
Which is why we have the crank length, for example, like as some probably say, yeah.
Okay. Cool. Well, if you don't have any other questions, thanks again for this fascinating talk. And
thank you. Like, yeah, that's sorry to interrupt you here. Yeah, please connect with me. I would love to kind of like connect with you guys. This is my first time that I'm like with this whole group. Like, I'm so sad that I never heard of this throughout my whole PhD. I only heard about this like a couple of months ago. I think it's really cool that you guys exist. And even though I'm moving to London, I hope I can stay connected with you guys.
Wonderful. Thanks.
Thank you, guys.